This is the answer key for the Algebra 2, Unit 2 test review guide. Unit 2 covers linear functions and absolute value functions. Because linear functions were covered so heavily in Algebra 1, we won't do a lot with the linear functions. This unit will be most heavily covering the absolute value functions. But we're going to contrast and compare some things with the linear and absolute value functions, and so we'll definitely ask you some questions that are related to linear functions. Now, notice that this first question specifically asks about the equations of linear functions, and it asks you to give two specific characteristics. And the first thing that you want to remember about linear functions is that the x does not have an exponent or it would be more accurate to say that it doesn't have an exponent other than 1. So basically, in a linear function, the only x that you have should just be x to the first power. The other thing that you want to look for is to make sure that x is not in a denominator. If x has a different exponent or is in a denominator, that makes it a different type of function. But if you're dealing with just x to the first power, not in a denominator, then the function will be the linear function. Now, again, we're going to look at just the idea of the equation, and this time we want to specify the equation of an absolute value function. And the one most important thing for an absolute value function is that x has to be inside the absolute value symbol. If x is outside the absolute value symbol, if you have absolute value symbol but it doesn't have an x inside of it, then it's not an absolute value function, because the x has to be placed where the type of function is affecting the x. So here are some examples of some equations and some graphs, and you're asked to make an indication for each one as to whether it's linear or absolute value or some other type of function. And so because we haven't learned about other types of functions yet, we're just going to say other rather than specifying these other types of functions. So this first one, notice that the x has an exponent on it and there's no absolute value symbol there. So we're going to say that this is other. It's some other type of function. In this equation, you've got an x and a y. You could rewrite this equation in y equal form, and even if you did so, x would not be in a denominator and would not have an exponent on it, so this is a linear function or a linear equation. Now, just because this equation has an absolute value symbol in the equation, the x is not inside of it. Notice that the x is x to the first power, is not in the denominator, so this equation is also linear. And this is really the equation to watch because it's the one that's meant to kind of trick you because of the absolute value symbol being around just a number and not the x. In this equation, x is in a denominator, and so therefore it's not linear nor is it absolute value. So we're going to say that this is other. In the next equation, we have x inside of an absolute value symbol. So this is an absolute value equation. In this next one, your x is x to the first power, and it's not in a denominator. Therefore, this one is linear. In this next function, you have x inside the absolute value, and therefore this is an absolute value function. And again, in this next one, you have x inside the absolute value, so this is another absolute value function. So those are the equations that we've got in this problem, but let's take a look at the graphs. Remember that the graph of a line is just a straight line. It doesn't have any bends or curves in it. So these first two graphs are both linear. This third graph does have a curve, and it's not V-shaped. Therefore, this is another type of function. So we're going to say other. And this last one is V-shaped. The V is facing down, or we would say in math that it opens down, but it's still V-shaped. It still has that vertex and the straight sides, and so this is an absolute value function. Now, question 4 gets into the equations that indicate transformations to the absolute value functions. And you can either have a leading positive or negative. If there's a number, your stretch or compression, you can add or subtract a number inside the absolute value or outside the absolute value. And each of those things transforms the graph in a different way. So let's take each of those one by one. If the beginning of the function is positive, when it's written in the transformation notation, then it doesn't flip, and the A by itself then indicates either a vertical stretch or compression. So I'll start by writing vertical stretch or compression. But remember that with the vertical stretch or compression, if A is a number that's less than 1, then it's a compression. Usually that'll look like a fraction, 1/2 or 2/3 or something. And if A is greater than 1, it's a vertical stretch. If A is negative, the A still affects the number part of A still affects the stretch or compression, but the negative sign itself indicates that you have a flip over the x-axis. If you are adding a number inside, and let me back up a second. Remember that in the equation here, that H is inside the absolute value symbol. And remember that we said that insiders lie. So if H is inside the absolute value symbol, and we're adding H, then that indicates a shift to the left. So the inside number added or subtracted is a shift left or right. It's a horizontal shift. And if it's plus H, it's a shift to the left. And if it's minus h, it's a shift to the right. And then the k is the number being added outside the absolute value symbol, added or subtracted. And if it's being added, that's going to be a shift up because outsiders don't lie. So it's a shift up. And then minus k is a shift down. And if you take that transformation formula where there could be a number multiplied in front of the absolute value, you could have a number added or subtracted inside the absolute value, and you could have a number multiplied or added or subtracted, outside the absolute value. If you look specifically at h and k, the vertex of the entire absolute value function is h comma k. And so you just take a look at those numbers, h and k, the one inside the absolute value and the one outside the absolute value, and the vertex of your V shape is going to be at the point hk. Now remember that equations of parent functions are the simplest form of an equation that you can write. And so the equation of the parent function of this linear equation is f of x equals just x. No exponent other than 1, and no x in a denominator. So just f of x equals x is a linear parent equation. In number 6, again, asking about the equation of the parent function, this time we're looking at an absolute value function. So this is absolute value. And the equation of the parent function, the most basic equation of an absolute value function, just has the absolute value of x. So let's draw a transformation of the absolute value function. The first thing that you want to do is be able to draw a parent graph of the absolute value function, or a graph of the parent function. Now remember that the parent function of the absolute value function has a vertex at 0, 0, that the right side of the graph has a slope of 1, which means you go up 1 and over 1, and it goes in this direction up and to the right, and that the left side of the graph is symmetrical to the right side, and it has this slope and goes up and to the left like that. So that's the parent graph of your absolute value function. And what we want to do to that graph is take that same graph, reflect it over the y-axis, vertically compress it by a factor of 2/3. We want to shift it left 1, and we want to shift it down 2. So remember that reflected over the x-axis is going to make that V shape open down instead of up. That the vertical compression factor that says here factor 2/3 means that the sides of the absolute value are going to have a slope of 2/3, and the shift left 1 takes that vertex and shifts it to the left, and shift down 2 units takes the vertex and shifts it down 2 units. I would recommend starting by shifting the vertex first. So shift the vertex left 1 and down 2. So left 1 and down 2 puts my vertex right there. Now remember that we're going to have a V shape that opens down. And so if we want that V shape opening down, then what we want to do is give ourselves this slope of 2/3 so that the graph opens in that direction. So I'm thinking here down 2/3 to there, and my next point is going to be there. I don't have any more space to go in that direction, but remember also that this graph is symmetrical, so I can go down 2/3 in the other direction and give myself another point here. So the point at -1, -2 is my vertex. I've given myself my slope of 2/3, which gives me that vertical compression, and I've shifted left 1 and down 2. So now I can connect the sides of the function, and there is my absolute value function transformation. Now, if you are working with a graphing calculator, you can use the buttons alpha and then window. And when you do alpha and then window, really what you're doing is you're giving yourself that F2, the green F2 above the window button, and that gives you a menu with some mathematical functions there, and you'll see that the first choice, number 1, is absolute value. And when you type that combination, alpha window number 1, it gives you absolute value symbol with the little blinking cursor inside that's basically saying type something inside. So if you want to graph these functions using a graphing calculator, what you'll want to do is go to your y equals screen and type exactly this into your y equals screen. Absolute value of x minus 3, and then you want to hit right arrow to get out of the absolute value sign and type your +1. I'm going to talk you through graphing all 3 of these graphs using transformations though. You are welcome to use the graphing calculator. One more note about the graphing calculator: if you're not sure what points to graph, after you've done alpha window 1 and typed your equation into the y equals screen, then you want to do second graph. And second graph gives you a table of x and y values so that you can graph the points of the graph. Now, I'm going to graph these graphs using transformations. So for example, in this function, because I've got -3 inside, that's going to be a shift to the right. And because I've got +1 outside, that's a shift up. Shift up 1. And so when I do these shifts, I'm going to shift my vertex. So the vertex of the parent graph starts at 0, 0. I'm going to go to the right 3 and up 1 and put my vertex of the transformed function at 1 at the point 3, 1. Notice also that there's no a value and there's no negative sign in front. That means that your slope doesn't change from the parent function, and so your slope on the right is going to be 1, which is up 1 and over 1, and your slope on the left is going to be symmetrical to that slope, and so your slope on the left looks like that. And there's your absolute value of x minus 3 plus 1 graph. Number 9 has 4 transformations. Let's look at them individually. First of all, it's going to be a flip over the x-axis. It's going to have a vertical stretch, which means that changes the slope. It's going to shift left. And it's going to shift down. I'm going to start with my shifts. So I'm going to shift left 4 and down 3. 1, 2, 3. I'm flipping that over, and it looks like I'm going to run out of space. My vertical stretch is a factor of 2, so remember that my slope is 2, so I'm going to go down 2 and over 1. And then on the other side it's symmetrical, and so my graph with that flip is going to basically look like this. In this third graph, we have a vertical compression, so the 1/3 there, that's a vertical compression. And the +1 here is going to be a shift left. So I'm going to shift left 1, but I don't shift up or down at all. So my vertex here is going to be at -1, 0. And my slope on the right is going to be up 1 and over 3. And so my points on the right are going to be there and there. And then remember that the left is going to be symmetrical to the right. And my graph ends up looking like that. So if you are working in your calculator on this problem, when you're typing the 1/3, remember that in your calculator, you want to type alpha y equals and enter. And what that gives you is a fraction with the cursor and little boxes waiting for you to type the numbers in. And that way you can type your 1/3 so that it looks exactly like it does in the equation here. Now, this next question asks you to get a little bit creative. You're creating an absolute value function with a certain number of stipulations. Remember that absolute value functions are the V-shaped functions, just like we drew in the previous 3 problems. And you're asked to give your function a domain of -infinity to +infinity, or all real numbers, and a range that goes from -infinity to 4. And think about this. If your range goes from -infinity to 4, it has to have a top at 4, and the bottom has to go forever. And so that's going to be an absolute value that opens down. Those are the only specifications that we're giving you, and you can choose your own slope or how far shifted left or right you want, as long as that vertex at the top of the function is at 4 and that the function opens down. So I'm going to randomly choose to put my vertex here, and then I'm going to give myself a slope of 1 just because it's fairly easy. Just remember that your right and your left sides should be symmetrical. And your graph can look like that. Remember that your vertex can literally be anywhere along this line here. And as long as it opens down, you've met the qualifications. Now, because I chose a slope of 1 for my graph, it asks for my equation, so f of x equals negative for the flip, that means that the v is opening down, and then absolute value of, well, I shifted right 2 and up 4. So x minus 2, because insiders lie, that shows my right shift. And then plus 4 is that up 4, so that the vertex is up at 4. And so that's the equation for the graph that I drew. Your graph is going to have, or your equation is going to have different numbers in it, depending on where you place the vertex and what slope you chose for your graph. The things that have to be in your equation are the negative because of the flip, and the plus 4 because it has to be shifted up 4 to make the range negative infinity to 4. Now, for 12, 13, and 14, we're graphing it says absolute value inequalities, and then number 12 is not an inequality. Do you see that? Crap. And what your slope. Now, for 12, 13, and 14, you are asked to graph absolute value inequalities. Remember that when you're graphing an inequality, you start by graphing similarly to how you would have graphed an equation, except that instead of an equal sign, you've either got a less than or greater than sign, or less than or equal to, greater than or equal to. And so you're going to graph either a dotted or solid, a dashed or solid line, and you're going to shade either up or down, and we'll talk in a minute about what that's going to look like. So I'll start with this first one. Again, you can get the basic shape and plot points for this as if it were an equation using your calculator, typing that into your y equals screen, and then pressing the button second graph in order to graph the exact points here. I'm going to talk about the transformations again. I see that this is going to open up. It's going to be a V shape that opens up because there's no negative sign in front of the absolute value. The plus 2 inside means that I have a shift to the left, 2. And the minus 3 outside of the absolute value says that I shift down 3. And so I'm going to take my vertex, which was at 0, 0 in the parent graph. I'm going to shift it left 2 and down 3. Well, that was the class change music, and so I turned off the recording for just a minute while we listened to some more U2. And now I'm back, so we shifted to the left 2 and down 3. Because there's no number in front of the absolute value, there's no A number that changes the slope, our slope for this is just going to be up 1 and over 1. So the slope on the right is 1, and the slope on the left, remember the left is going to be symmetrical to the right. But there's going to be a difference here, and I want you to compare number 12 to number 13. And see that in number 13, it says less than or equal to, but in number 12, it's just less than. And when it's just less than, when you graph the line that makes the absolute value, you're actually going to graph it as a dashed line. You're going to keep the same slope, you're going to go in the same direction. Everything else about the transformed graph is going to work the same way, except that it's going to be a dashed line and not a solid line. When we get to number 13, it'll be a solid line because of that equal, half of an equal sign there. The other thing that we need to remember to do is to shade. And anytime that it's a less than inequality, you shade down in a downward direction. It doesn't have to do with inside or outside. It's just in the direction of down. And anytime it's greater than, you're going to shade in the direction of up. So when we get to number 14, which has a greater than, we'll be shading up. But for now, that's number 12 with the dashed line and shading down. Let's work on number 13. And so in number 13, I have a flip because of the minus. So this minus right here reminds me to flip. I have a vertical stretch. That means that my slope is going to be 2. And my minus 1 on it, the inside is going to be a shift to the right. So I'm going to take my vertex and shift the vertex to the right 1. And notice that there's no up or down shift, and so that vertex is going to be on the x-axis. My slope is, well, with the flip, the V shape is going to open down, and the slope is 2, so it's going to go like this, and then symmetrical on the left. And because of that or equal to sign there that we just talked about a minute ago, this is going to be a solid line. And because it's less than, the shading is going to be in the downward direction. Again, it's not about inside or outside, it's shading up or shading down. So compare numbers 12 and 13. Make sure you understand why 12 has a dashed line and 13 has a solid line. Make sure you understand why they both shade in a downward direction, because they're less than. And now let's take a look at number 14. So number 14 is going to have a vertical compression. That means that the slope of the line is going to be 2/3. The +3 on the inside means a shift to the left. And the -4 on the outside is a shift down. So I'm going to start by shifting my vertex 3 to the left and 4 down. And so my new vertex is at -3, -4. There's no flip here, so when I draw my slope, I'm going to be going up and to the right 3. So up 2 and to the right 3, up 2 and to the right 3. And then just to kind of give myself a little guidance, because the left has to be symmetrical, I know that it's going to be approximately there. Now, because this is strictly greater than and not greater than or equal to, I'm going to be graphing a dashed line. So my graph is going to end up looking something like this on the right, and on the left you're just going to need to kind of eyeball it a little bit. Just remember that it should be V-shaped. And because it's greater than, the shading is going to be in an upward direction this time. And compare this greater than in number 14 to the two problems that had a less than in 12 and 13. And just make sure you understand the difference in the shading. So in number 15, we continue to talk about transformations. And what you want to start to do is to recognize these transformations. And as I've been graphing, I've been mentioning them, and so you should at least be familiar with them. Remember that inside of the absolute value, that's going to, if a number is added or subtracted inside the absolute value, that's going to indicate a shift to the left or to the right. And if it's minus, it's going to be to the right, and if it's plus, it's going to be to the left. And because that's somewhat counterintuitive, we're going to use the little phrase, insiders lie, meaning that it's going against your intuition. And so this one, because it's minus, it's a shift to the right, 3. And remember that on your test, I expect you to use the word shift. If you don't, I will take off a point. So don't just write right 3, but write shift right 3. Now in this equation for letter A, there are no other transformations. There's no shift up or down. You don't have any stretch or compression, and there's no flip. So shift right 3 is your only transformation there. If you were to take the parent graph and shift it right 3, the vertex stays on the x-axis, but it moves to the right 3, and so your vertex is going to be at 3, 0. And remember that your axis of symmetry is the line that you could fold the paper over and the graph would transform on top of itself. And so the axis of symmetry is always going to be a vertical line. So it starts with x equals, and it's going to have the same number as the x value of the vertex. So your answer for the axis of symmetry is x equals 3 because the vertex is 3, 0. Now in letter B, I see 4 different transformations, and I'll go through them one at a time. The minus sign, remember, you want to treat differently than the 2 that's multiplied. So your eye sees -2, but because the minus is about the flip and the 2 is about the vertical stretch, you have to look at them separately. Then this -2, or subtracting 2 inside and adding 5 outside, those are your shifts. The -2 inside is your right-left shift, and your +5 outside is your vertical shift. So let's start with the flip. And remember that you have to say flip over what? So in this case, we're going to flip over the x-axis. That's the minus sign before the initial 2. Then that 2 that I highlighted in blue that is being multiplied, that's going to be a vertical stretch. Remember that it's a stretch if it's a number bigger than 1. And so it's a vertical stretch. Remember that you also have to tell us the factor. In this case, it's 2. Then your shift, your sideways shift, because it's minus and insiders lie, it's a shift to the right. And it's shifted to the right too. Outsiders don't lie, and so your outside +5 is going to be a shift up 5. Now if you think about this, if you took the vertex of the parent graph and shifted to the right 2 and up 5, the point that you get is the point 2, 5. So your new vertex is going to be 2, 5. And the axis of symmetry, x equals 2, because 2 is the x value of the vertex. So this number and this number are always going to be the same. In part C, I've got 3 transformations. I have this 1/2 that's multiplied at the beginning. I've got the +2 on the inside, and I've got the -6 on the outside. So the 1/2 at the beginning is a vertical compression. And the factor is, wow, I can't spell. The factor is 1/2. So remember that you need to tell us it's a vertical compression and that the factor, that it's compressed, and it's just the number that's multiplied. Your +2 on the inside is a shift. Remember that insiders lie, so this time it's a shift to the left, 2. And the -6 on the outside, that's going to be a shift down, 6. And again, if you start with the parent function, that has its vertex at 0, 0, and you shift left 2 and down 6, your new vertex is going to be at the point -2, -6. And your axis of symmetry, x equals -2, I get that number from here. And in problem D, again, I see 3 transformations. I have this minus that's multiplied out in front, and that's a flip. I have the +4 on the inside of the absolute value. That's going to be your right-left shift. And I've got +6 on the outside, and that's going to be your up-down shift. So the minus at the beginning is your flip over the x-axis. The +4 on the inside is your shift. Remember that insiders lie. And so this is going to be a shift to the left 4. And then the +6 on the outside, outsiders don't lie. And so this is going to be a shift up 6. So if I move the vertex to the left 4 and up 6, the vertex, the coordinates of my new vertex or my transformed vertex are going to be -4, +6. And the axis of symmetry there is x equals -4. Now, in number 16, we have an absolute value function, and we're asked to give the domain and the range. Remember, and this might be a little bit of a trick to help you, that your domain is always going to be the number on the left first and then the number on the right, and that your range is always going to be the number at the bottom first and then the number at the top. And so if I'm thinking about the domain left to right, this graph is going forever left and forever right. And so my domain is going to be from -infinity to +infinity. And remember that the way we say that is either -infinity to +infinity, or you can actually say the words all real numbers. But on the test, we'd like you to give this interval notation. Now, the range is going to be looking from the bottom to the top. Now, the bottom-most part of this graph is right here where I'm drawing that yellow line. And remember that your range is y values. So that yellow line is where y equals 1. But notice that the graph is going forever up on both sides. And so for your range, you want to start at y equals 1 and go up to infinity. Now, infinity will always have the round parentheses, but the 1 right here, that y equals 1, there is a point, the vertex, and it has the y value 1, so the y value 1 is a part of that graph, it's included, and so we're going to use the square bracket to indicate a point that's included in the range. Now, notice that number 16b is not a function. It's not a function because it wouldn't pass the vertical line test. We're still going to be able to ask you about the domain and range, and it still has the shape of the absolute value functions, but understand that we're not going to use the word function when we're talking about this graph in 16b. So we're looking at the domain and range, and for the domain, the leftmost value is this x value at x equals -3, but on the right, it goes forever. And so your domain for part B is going to be -3, including -3, all the way to +infinity. And we use the square bracket for the same reason that we did with the range in part A. For this one, the range at the bottom our graph goes to negative infinity, and at the top, our y values go to positive infinity. And so our range in this question is going to be all real numbers, negative infinity to positive infinity. Now, in number 17, you'll see the graph of an absolute value function. Hint, if you forget the name of the function family, absolute value, turn to the front page of the test. The front page of the test says, this is a test about absolute value functions. And so if you are not sure about the name of the function family, and this probably would apply to all of your tests for units 2, 3, 4, 5, 6, 7, 8, and 9, if you forget the name of the function family, it should be on the front of the test as the title to the test. Just a little piece of advice. So in this case, the function family is absolute value. And the equation of the parent function, which we talked about on page 1, is absolute value of x. Remember, when you're giving the equation of the parent function, it's the parent function. It's not the equation of the graph you see here. It's just the parent equation. And remember that it's a function equation, and therefore you should use function notation. So the function notation is this f of x. So just remember to write f of x equals and then absolute value of x. Now your domain, let's practice domain again. On the left, it goes to negative infinity. On the right, it goes to positive infinity. And so your domain is, again, going to be all real numbers. Your range starts at the bottom and goes up to -3. Well, down here at the bottom, it's negative infinity. Remember that we're looking at y values. And at the very top of the graph, that's y equals -3. And so our range goes from negative infinity to -3 inclusive. For every absolute value function, your domain will be all real numbers. Your range will be either positive or negative infinity in one spot and a number in the other spot, and the number will always have a square bracket. The other thing to remember about every absolute value function is that the vertex, which is here -2, -3, you can fill that in over here if you want at this point, is also going to be either a minimum or a maximum. In this case, it's a maximum. And so let's say that the max here is the point -2, -3. Remember that you want to write either the word min or the word max so that we know that you know which you're looking at. Now this graph is increasing here and decreasing here. Think about an ant crawling on the graph from left to right. He's going uphill on this side of the graph and downhill on the other side of the graph. So he goes uphill, he changes at x equals -2, and then he goes downhill. So the change happens at x equals -2. So my increasing is from negative infinity to -2, and at -2 he changes and decreases from -2 to positive infinity. And I want you to double check your answer for decreasing and make sure that you've got positive infinity there, because the x values go to the right and you aren't paying attention to the down part when you're writing the answer to decreasing. You're looking at the fact that the x values are going to positive infinity. Now, both sides of that graph are going down. Therefore, your end behavior is negative infinity for both right and left ends. for an absolute value function, your end behavior will be the same for both sides, right and left. Now, the axis of symmetry is always going to be x equals the same x value from the vertex. That was -2, so my axis of symmetry is -2. There are no x-intercepts, so I'm going to write none, or I can write NA. Do not write null set. Your y-intercept is 0, -5. That y-intercept is right here. And remember that your zeros are going to be the same as your y-intercepts. And so if there's no x-intercepts, I'm sorry, your zeros are the same as the x-intercepts. So if there's no x-intercepts, there's no zeros. So sometimes you're going to be given a graph and asked to solve a graph. And just remember that the solution to a graph is always going to be the x-intercept. Now, sometimes the x-intercept is not going to be exactly a whole number. So in this case, your x-intercept, I would say, is about 0.7 or 0.8. And so you want to write the solution as x equals 0.7 or 0.8. Sometimes there's no x-intercept at all. So in this graph, the function never touches the x-axis, and so you're going to say no solution. In this graph, you'll see that this is also no solution because there's no x-intercept. In this graph, we have two solutions, one here and one here. And the first one I would say is, again, about 0.5, maybe 0.6. And the other one is, let's say, 3.5. In this graph, your x-intercept is here at x equals -1. In this graph, there's no x-intercept, therefore there's no solution. This graph again has two solutions, one here and one here. So x equals -5 and x equals -1. Now, this graph obviously has one solution, but I want you to think about if the x-axis, if I hadn't cut the graph on the screen where I cut it, and the x-axis were extended to the right and the graph also, then there would be another x-intercept here. And think about the symmetry of this. If the vertex is right here, and this solution is 1, 2, 3 spaces away, then let's say that this solution would also be 3 spaces away, and this one would be x equals 7. Now, we won't put something so complicated on your test next week, but I do believe that you should be able to understand that even though the graph doesn't show both solutions, that there are two solutions, and that you can come pretty close to making an educated guess as to what the other solution is that's not shown on the graph. Now, you might want to pause the video for a minute and find your notes for Lesson 2, the Lesson 2 notes, and on the very back of the page, or the last page, there's a section that talks about special cases for solving absolute value inequalities and equations. So grab your notes, turn to that last page, And the first thing that we wrote is that if you have the absolute value of anything, so I'm just going to put a question mark because it doesn't matter what's inside the absolute value, but if you've got the absolute value isolated and it is equal to a negative number, then you have no solution, because an absolute value is always positive. And so if you work out a problem and you find that the absolute value isolated is equal to a negative number, stop working, because there's no solution to that problem. I'm going to skip this empty box underneath that for a minute, because the next two things that I gave you were the special cases for inequalities. And first of all, any absolute value that is set greater than a negative number is going to be all real numbers. The reason for that is that any absolute value, so if you're thinking about the left side of this equation, any absolute value is always positive. And therefore, it's always greater than any negative number. So if you isolate the absolute value and it's greater than a negative number, then your answer is going to be all real numbers, because any number could substitute for x in the absolute value. The absolute value is going to force the answer to be positive, and a positive number is always greater than a negative number. Now, the other way around, if you have an absolute value of anything that's less than a negative number, then your answer is going to be no solution. And again, that is because an absolute value is always positive, and a positive number is always greater than a negative number, and it can never be less than a negative number. A positive number is always greater than a negative number. And if you're not sure, just ask yourself if you would rather have positive money or negative money. Negative money is like having debt, and positive money is like walking around with money in your pocket. And so the positive money is always greater than the negative money. Positive number is always greater than the negative number. Now, the last special case I gave you was when you have an absolute value of anything that's set equal to 0. When you isolate the absolute value, if you get 0, you will have a solution, but there will only be one solution. Now, you don't write the words one solution. What you do is you compute using just one equation, and you're going to get x equals and then some number for your answer. So let's practice some examples of equations and inequalities. Remember that your first step of solving any equation or inequality with an absolute value is to get the absolute value isolated. And in number 20, the absolute value is already isolated. Once it's isolated, you want to split the equation into two separate equations without an absolute value. Write the inside of the absolute value exactly the way it's given at the beginning, and then set that equal to the positive number that's on the other side of the equal sign. So those two numbers should be the same. And then write that whole thing again, but instead of positive 7, you're going to say equals negative 7. So take that number that's on the other side of the equation and write it again, but as a negative number. Then you're going to solve both of those equations. So I'm going to subtract 2 from both sides. Negative 3x equals 5. And then I'm going to divide both sides by negative 3. And so here, x equals negative 5 over 3. And then on the other side, negative 3x equals negative 9, and I'm going to divide both sides by negative 3, and x is equal to positive 3. So my two answers to number 20 are negative 5/3 and 3. In 21, I need to isolate the absolute value first, and so I'm going to add 9 to both sides. And when I do that on the left, I get just the absolute value all by itself. And on the right, negative 11 plus 9 is negative 2. And now I have a special case. Remember that the special cases happen when you've got the absolute value isolated on one side and a negative number on the other side. And an absolute value is always positive, and a positive number cannot be equal to a negative number. And so this problem is going to have no solution. Once you have decided that the answer is no solution or all real numbers do not keep working, you could force this problem to give you an answer, but the answer would not be correct. Now, in this problem, remember that you want to kind of think about this as negative 4 minus 2, let's say z equals negative 10. And if I were your Algebra 1 teacher and I gave you this equation, and I'm just saying I want to isolate the z like I want to isolate the absolute value, then I would start by adding 4 to both sides. I dropped my pen. I would start by adding 4 to both sides, and then I would divide by negative 2. Now, obviously, this isn't the problem that we're working out. And I'm going to move that thinking over to the side there so that I can work in this space underneath the problem. You're going to do the same process to isolate the absolute value here. You're going to start by adding 4 to both sides. Bring down your negative 2 times the absolute value of x plus 5. That equals negative 6. And then you're going to divide both sides by negative 2. And now you have the absolute value of x plus 5 is equal to positive 3. Write your two equations. X plus 5 equals 3, and x plus 5 equals negative 3. Solve both of those equations by subtracting 5. 3 minus 5 is negative 2. Negative 3 minus 5 is negative 8. And your answer then is x equals negative 2 and x equals negative 8. In number 23, in order to isolate the absolute value, I'm going to add 7 to both sides. And so on the left, I have the absolute value of x plus 4 is equal to 22. Now my absolute value is isolated, so I can write my two equations. X plus 4 equals positive 22. X plus 4 equals negative 22. I'm going to subtract 4 to solve, and 22 minus 4 is 18. Negative 22 minus 4 is negative 26. In this problem, in order to isolate the absolute value, I'm going to subtract 3. When I do that, I get on the left the absolute value of 5x minus 8. But on the right, I get 0. And remember that whenever you are solving an absolute value and you get 0, that is one of your special cases. So make a little star here for yourself to remember that if you get absolute value equal to 0, that equation is going to have one solution, not two. And so I'm just going to write 5x minus 8 equals 0, and 5x equals 8, and then x equals 8 over 5. And so my answer to this equation is just x equals 8 over 5. And in this last problem, to start isolating the absolute value, you're going to add 3 to both sides. And then you bring down the 6 times absolute value of 7x plus 1. The 3's cancel, and all of that equals 24. Then divide both sides by 6. And now you have the absolute value isolated. Absolute value of 7x plus 1 is equal to 4. You're going to break that into two equations. 7x plus 1 equals positive 4, and 7x plus 1 equals negative 4. Solve each of those equations. I have a little bit more space than you do. 7x equals 3 because I subtracted 1, and then x equals 3 divided by 7, or 3/7. Over here, 7x is equal to negative 5. Negative 4 minus 1 is negative 5, and so x is equal to negative 5/7. So take a look at your work, double check these answers, make sure you understand everything, and then we'll go on to number 26. Now we're going to solve some absolute value inequalities. So we'll start with number 26. Make sure that you see the difference between the 6 problems we just did that were equations with equal signs, and these 6 problems that are inequalities that each have a greater than or less than sign, and they work somewhat differently when you get to the end. And you have to keep in mind that if you divide by a negative number, you reverse the sign. You also need to remember to graph your answer on a number line. Now, the way that this works the same as the equations is that you have to start by isolating the absolute value. You do that using the same process. And then you're going to end up solving 2 separate inequalities based on the isolated absolute value. Now, in this problem, the absolute value is already isolated, which means that it's on one side of the inequality all by itself. There's no numbers added, multiplied, subtracted, or divided with the absolute value. So I'm going to go ahead already and divide my problem into 2 parts. And I'm going to take the first part and write what's inside the absolute value, and then exactly the less than and 15 as it appears in the equation. And then on the other side, I'm going to write the same thing from inside the absolute value again, but this time I'm going to reverse the less than and make it greater than, and I'm also going to change positive 15 to negative 15. So notice that I changed 2 things here. I changed the less than to a greater than, and I changed the negative or the positive 15 to a negative 15. Now you're going to solve each of those. And so in this first one, I'm going to subtract 1 from both sides. And then I'm going to divide both sides by 2. And then in the second one, I'll subtract 1 from both sides again. And divide both sides by 2. And I end up with x is less than positive 7 and x is greater than negative 8. Now, remember that I'm only asking you to graph the two numbers, that you put the number that has lesser value to the left, so the negative 8 goes to the left, and the number with the greater value to the right, so positive 7 goes to the right. Both inequalities that are part of your answer are strictly less than or greater than. They don't have that little part of an equal sign there. And so you're going to use an open circle both at negative 8 and at positive 7. And I want you to think about first, x is less than positive 7. And so if you were just graphing x is less than positive 7, you would graph the graph in that direction. Now think about x is greater than negative 8. If you were only graphing x is greater than negative 8, you would shade the graph in that direction. Either the two arrows that you're shading are going to point toward each other or away from each other. They're never going to be doing one of each. And so in this case, you're going to shade everything in between and nothing outside of. Or I guess maybe I could do it in blue to keep consistent, but you're going to shade everything in between the negative 8 and the positive 7. Now in this next problem, you need to isolate the absolute value, and so we're going to start by adding 8 to both sides. And you end up with the absolute value of x minus 3 is greater than positive 4. Negative 4 plus 8 is positive 4. At this point, you've got your absolute value by itself, and so you're going to separate and use the x minus 3 without changing it, and then it's greater than positive 4. So basically the first time you're just writing the absolute value exactly the same but without you're writing the inequality exactly the same but without the absolute value symbols. And then the second time, all you're going to change, you're going to drop the absolute value, you're going to change the greater than to less than, and you're going to change the 4 to negative 4. Solve those two equations by adding 3. So x is greater than 7. And x is less than negative 1. So again, when you're graphing these on a number line, you want to keep in mind which one is bigger and which one is less. So the negative 1 is less, so it goes on the left, and the positive 7 is greater, so it goes on the right. Both are strictly less than or greater than, so it's going to be two open circles. And again, if you graph x is greater than 7, it points away. If you graph x is less than negative 1, it also points away. They should both be either pointing away or toward each other. And so this graph is going to be shaded going out. So there's 26 and 27. Now we'll look at 28. In 28, you're starting by dividing by negative 2. And when you divide by a negative, remember that you want to reverse the inequality. So dividing by a negative means that you reverse the inequality. And so this time we have x, the absolute value of x plus 4 is greater than positive 4. And make sure that you understand why that's greater than. Now I have the absolute value by itself, and so I'm going to break that down into two different inequalities. X plus 4 is greater than 4, and x plus 4, and now I'm going to reverse the inequality, less than, and change 4 to negative 4. Subtract 4 from both sides. Here I have x is greater than 0. Subtract 4 4 from both sides, and here I have x is less than -8. So -8 is the smaller number and 0 is the bigger number. Again, they're both strictly greater than or equal or less than. Neither of them have an equal. X is greater than 0, shades this way. X is less than -8, shades this way. And so this graph is also going to shade in the outward direction. Now 29 has a few more steps, so let's take a look at this. For this one, we want to start by subtracting the 2. Be careful and don't do 2 minus 4, because the 4 is multiplied by the absolute value, and we're going to wait, and then we're going to divide by the 4 later. But for now, we just want to subtract the 2 so that the 2's cancel. Bring down the minus sign with the 4. And then we're subtracting, so 10 minus 2 is 8. So now you've got -4 times the absolute value of 2x minus 1, which is greater than or equal to 8. Now I'm going to divide by -4 on both sides. And I get the absolute value of 2x minus 1 is less than or equal to -2. Make sure that you understand why the greater than becomes a less than when you're dividing by a negative. Now, here we have an absolute value on one side and a negative number on the other side. And remember, that's when our special cases kick in. Remember that an absolute value is always positive, and a positive number is always greater than a negative number. So absolute value cannot be less than any negative number. Therefore, this inequality has no solution. And you don't do anything beyond that step. You could force that problem to feel like it works, but the answers that you get would not be the correct answers. Now in number 30, you're going to divide by +3. You get the absolute value of x minus 2 is greater than -3. And again here, note that you've got the absolute value and a negative number on either side of your inequality. This time we've got a greater than sign. And the absolute value is always a positive number, and so here we have a positive number is greater than a -3. Every positive number is greater than any negative number, and therefore all real numbers satisfy that solution. And then in 31, we'll have a lot of steps here, so write small. We're going to start by subtracting the 5. I'm going to write that teeny. And so we're subtracting 5 from both sides, and we end up with 6 times the absolute value of 4x minus 3 is all less than 12. Then we're going to divide out the 6 on both sides, and we end up with this absolute value 4x minus 3 is less than or equal to 2. We have an absolute value is less than a positive number, so everything works at this point. It's not all real numbers, it's not no solution. So I'm going to split this into 2 different inequalities to solve. Leave the 4x minus 3 as it is. Leave the less than or equal to 2 as it is. And then in the other equation, don't change 4x minus 3, but do change. Less than becomes greater than or equal to, and 2 becomes negative 2. Solve both of those equations. So here I'm going to add 3 to both sides. And so I get 4x is less than or equal to 5, and x is less than or equal to 5/4. And on the other side, when I add 3 to both sides, I get 4x is greater than or equal to 1, and so x is greater than or equal to 1/4. So when you graph this, 1/4 is smaller than 5/4, and so it goes to the left. Both of the less than and greater than have the closed or the equal sign with it, and so you want to use a closed circle to indicate that 1/4 and 5/4 are included in what we're graphing. And then if you think x is less than or equal to 5/4, that would be this direction. X is greater than or equal to 1/4, that would be this direction. And so my whole graph is shaded in between the two numbers. So the last few problems we're going to get into talking about correlation and regression, linear regression. So let's start with the first true false. If two quantities have a strong positive linear relationship, that means a strong positive correlation, then the correlation coefficient can be represented by the number r equals 0.25. Well, that's going to be false because it says here strong. And 0.25, although it's a positive number, so it works with positive, 0.25 is not a strong correlation, and so we're going to say false. Strong would be like 0.9 or something very close to 1. In the second question, the second true false, number 33, if a positive correlation exists between height and weight, a person with above average height is expected to have above average weight. Well, the positive correlation means that as one variable goes up, the other one also goes up, that they both increase. And if you are saying that there is a positive correlation between height and weight, meaning as the height of a person gets taller, their weight increases, then you can expect that somebody who has an above average height will also have an above average weight. And so your answer here is true. And in this last one, the number 34, if a scatter graph shows very little scatter around a straight line drawn through the plots, it indicates a rather weak correlation. And it says here, very little scatter and weak. If there's very little scatter, it's a strong correlation. And so this one is also going to be false. Now, you might want to pause the video while you grab your cheat sheet for the graphing calculator regression steps so that you can learn them and make sure that you're comfortable with them. You will be given a clean copy of the cheat sheet on the day of the test. So you don't need to write notes on the one that you think you're going to be using, because we'll give you a clean copy of it in class. But you will have those cheat sheets, and so you can expect not to have to memorize the steps here, and just make sure that you are familiar with it enough to have worked some of these problems through, both the ones from the notes and the homework assignment, and then this one in the review guide. And if you want more, just ask and we can give you some more to practice with, but you're going to be using the steps listed on that sheet. So the first thing that you want to notice when you read well, let me read the problem with you. The following table shows the winning jumps in the men's long jump event at Olympic Games since 1968. Use 1960 as x equals 0. So the first thing that I want to point out is that if 1960 is considered the beginning of time for this problem, 1960 is year 0, you want to change, before you start typing anything in, you want to change each of the years to how many years it is after 1960. So for example, 1968 is 8 years later, 1972 is 12 years later, 1976, 16 years later, 1980 is 20 years later. Remember that we're thinking how many years after 1960. 1984 is 24 years later. 1988 is 28 years later. 1992 is going to be 32 years later. 1996 is 36 years later. 2000 is 40 years later. 2004 is 44 years later. 2008 is 48 years later. And 2012 is 52 years later. When you type these numbers into your graphing calculator, it will change the problem drastically if you use the actual year instead of these numbers that we just computed since 1960. So be careful that you don't forget that part of the problem and convert anything that might be given to you as years into, if it says 1960 is x equals 0, make sure that you make those conversions. Now, in your calculator, you're going to press stat, and then enter. And you want that first choice enter, which is going to take you to the screen where you have your L1 and L2 and so on. And you want to put those numbers that we computed for the year. So these are the year, and you're going to type in that 8, 12, 16, and so on. And in the second column under L2, you're going to type the numbers under the results. And so those are the numbers that are going to be like 8.9 and 8.24 and 8.35 and so on. You might want to pause the video while you do that. The other thing that you want to do once you have entered all those numbers into your calculator, into the stat screen, is that you want to go back and double check that all of your decimals are entered correctly. If you enter even one of the numbers somewhat off, even if it's off by a part of a decimal place, what you'll find is that your answers will be slightly off from what we're giving you in the answer key, and you'll probably be confused as to why. And it may be as simple as you type something wrong, but at some point you may find yourself wondering if you truly understand what's going on. Now, before you can answer part A, which says write the equation of the line of best fit, you actually need to look at the graph of the scatter plot without the line. So what you want to do then, I'm going to write it up here, is you want to press second and y equals, and you're going to see that menu that says stat plots, number 1 plot off, number 2 plot off, number 3 plot off, and so on. And you want to press enter to choose plot 1, and then you want to press enter again to turn plot 1 on. Now your screen should say at the top plot 1, plot 2, plot 3, then next line is on off with the on still blinking. And then next to type, make sure that your calculator defaulted to the scatter graph looking plot and not the bar graph or the box and whiskers plot or the line graphs, etc. Your X list should be L1. That means you typed your X values into L1. Your Y list should be L2. That means you typed your Y values into L2. And it doesn't matter which mark you choose. I always just leave it set to the little box, but you can change it to a plus or a dot if you want to. Don't forget that to look at the graph, you don't want to press graph. In this case, you want to press zoom 9, which makes the data fit to the screen that you're looking at, because most of these numbers are not less than 10, at least your x values are not less than 10. So if you just pressed graph, what would happen is that most of the dots in your scatter plot would be off of the screen of your calculator, and you wouldn't see them, and you would wonder what you had done wrong. So when I look at my graph, that first dot, and you might want to make a note of this, that first year in 1968, his score was much higher than any other score throughout that time frame. Okay, and so yeah, that dot looks a little out of place, but it is actually accurate to the data that we have here. So part A asks you to write the equation of the line of best fit. But before we do that, we want to remember that we're also eventually going to talk about the correlation coefficient. If you look down a little bit farther, it asks about the correlation coefficient. So while we're computing the equation of the line of best fit, we also want to turn on the diagnostics. So remember that to turn on your diagnostics, what you want to do, turn on diagnostics, is find the button that says mode, and then you want to arrow up until you see stat diagnostics, and you want to turn stat diagnostics on. And when you've turned stat diagnostics on, now when you compute the line of best fit, it will also compute the R number that we need to use to find the correlation coefficient. So in order to compute the line of best fit, you want to press stat again. And this time you want to right arrow to the menu that says calc. And you want choice number 4, which is linear regression. And what you see in the screen that you get is XList L1, because you put your X's in L1, YList L2, because you put your Y's in L2. Frequency list, we're not going to do anything with a frequency list, so you can skip over that one, but I want you to arrow down to where it says store regression equation. And when you've got your cursor next to store regression equation, you want to press alpha, the green button over on the side, and trace, which is in the top row. So alpha, trace, and you'll see a bunch of Y1, Y2, Y3 lists of the Y options for your Y equals screen. If you just press enter, next, it'll automatically choose Y1 for you. And you'll see that now it says store regression equation ... Y1. And what that means is that once you've computed the equation of the line, the calculator will automatically save that equation in the Y1 equation spot in your Y equals screen, and it'll automatically graph that equation of the line. You want to down arrow again to calculate and hit enter. And your calculator thinks for a quick second, and then it gives you a screen that looks like this. It says y equals ax plus b. Remember, that's linear because x doesn't have an exponent or is not in a denominator. It says a equals negative 0.0035227273, and so on. And then B equals 8.626515, all, and so on. And then it says R squared equals 0.071394, and so on. And R equals negative 0.26711983, and so on. Now remember that we don't need the R squared number. We're going to use the rest of these numbers. So let's start with looking at A and B, where A is your slope and B is your y-intercept. And you're going to rewrite that equation here for part A as y equals negative 0.00, and remember significant digits. You want the first two significant digits, negative 0.0035, x, and then plus b, so it's going to be plus 8.6, the 2 rounds up to a 3 because of the 6 after it. So that's your best fit equation. And now if you just press graph, don't zoom anything, but just press graph, you should see a line that's being graphed through the data that you have, through the scatter plot that you looked at earlier. Now, the slope of the line, remember that the slope of the line is this number right here, tells you about, what does it tell you about the average rate of change in length of the winning long jump? And because it's negative, it tells me that it's going down. And because it's a very, 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 very small negative number, it says that it's going down very slightly over time. So let's say that it decreases slightly over time. And then it says, use the line of best fit to predict the winning jump for the 2016 Olympics in Rio. And so 2016, remember that we're using x equals the number of years after 1960. And so here, x would equal 56. And what we want to do then is go back to your calculator. You should be in your graphing screen. So you're looking at the scatter graph, and you want to press second, and then trace. And you see the menu that has value 0, minimum, maximum, and so on. And you want number 1 for value. And when you choose number 1 for value, you get this x equals and then a blinking cursor at the bottom of the screen. And you want to enter that 56 number into the screen and then press enter. And it tells you that when x is 56, y equals 8.42924, and so on. Now remember that we ask you to round everything to 2 decimal places. And so here, the prediction is 8.42. Remember that you want to label, that should be 8.43, because I rounded it because of the 9. But remember that we want you to round to 2 decimal places and then label your answer. So in your chart over here under result, you'll see that all of these measurements are given in meters. And so what you're saying here is that the prediction for the winning jump in the 2016 Olympics is going to be 8.43 meters. I don't think I could jump that far, whether it's better or worse than the last person that jumped it. Now, in Part D, they ask you to use the line of best fit to approximate the year in which the jump should have been 8.47 meters. Notice here that 8.47 meters is a y value, and so you need to remember the process for finding an x value when you're given a y value. So what you want to do here then is to go into your y equals screen, And there's already an equation in y1 equals, so you want to arrow down to y2 and type just the number 8.47, and then press graph again. And what you'll see in your graph is the scatter plot, and both lines, you'll see it kind of looks like this. And I'm going to not do the scatter plot part, but you see the line of best fit, and then you see that horizontal line that you just drew. And the horizontal line is the 8.47. The next thing that you want to do here is press second trace, and then you want number 5 for intersect. So second trace 5, and then you want to press enter 3 times. So enter 3 times. And then what it'll show you is x equals 44.43. So your x value is 44.43 when y is equal to 8.47. But I want you to reread the problem and ask yourself, is my answer 44.43? No, because you're asked to give a year, and probably the year isn't year 44. So how do we know what year this is equal to? Well, year 44 is going to be 44 years after 1960. And so do 1960 plus 44, and your answer is going to be 2004. So your answer for part D is 2004. Now, this scatter plot has a negative correlation. It asks for the correlation coefficient, and remember that we said we're not using r squared. The correlation coefficient is just r, and we're going to round that to 2 decimal places, and so it's going to be negative 0.027. No, negative 0.27. I apologize. Now, that number is much closer to 0 than it is to -1. And so and you can tell by looking at your scatter graph that the points are scattered quite far from this line. And so we're going to say that this is a weak or even a very weak correlation, because the points are quite far from the line of best fit. Now this next question asks you to get just slightly creative, and it asks you to give an example of a positive correlation that has something to do with the Olympics. And so let's say that you were looking at a high jump instead of a long jump, and let's say that every year in the time that you were keeping records, every year the highest jump would get higher. That would mean that as the years get higher, the jump is getting higher. So that would be an example of positive correlation, because both values would be getting higher at the same time. So let me say that the high jump top jump increases every year. So now for number 36, which is the last problem, yay. Remember that what we said is that positive correlation means both values increase or decrease. They're both either high when the other one's high or low when the other one's low. Negative correlation means that as one quantity gets higher, the other one gets lower. And no correlation means there's really no relationship between the two values, and so you can't have any kind of correlation between them. And so if you think about this, let's say that the temperature outside is being correlated to the number of hot chocolates sold. Now, when the temperature goes up, do you want to drink hot chocolate? I mean, most people want to drink hot chocolate all the time, but you are more likely to want to drink hot chocolate as the temperature is going down, especially if you're sitting outside at a football game on cold bleachers, just saying. So as the temperature goes down, you would expect the number of hot chocolate drinks to go up, and that's a negative correlation. One quantity is going down and the other quantity is going up. In part B, you're looking at the number of absences and their grades. I think I used that as an example in class. You would assume that if a student is absent more, that their grades would probably be a little bit lower. Now, obviously, these are trends or tendencies. We're not saying that every student that has high absences has low grades, or that every student that has no absences has high grades. That's obviously not true every time. But if you looked at a large number of students, you could probably correlate students with chronic absentee problems to students who have low grades. So as the number of absences goes up, you would expect the grades to tend down. So that's also a negative correlation. In part C, the number of hours you work and your paycheck, you would think that if you work more hours, your paycheck would go up. And if you work fewer hours, your paycheck would go down. Since both quantities are doing the same thing, that would be a positive correlation. If you spend a lot of time working out, meaning the amount of time that you're working out goes up, what do you expect to happen to your body fat? You would expect that your body fat would go down. The quantities are doing the opposite thing, and so that's a negative correlation. If I were to correlate the price of a computer and the price of a cup of coffee, if a computer is more expensive, is a coffee going to be more expensive? No, there's really no correlation between the price of a computer and the price of a cup of coffee. Oh, I think we used F in class as well. The amount of gasoline that's in your car and the distance you can go without refueling. The more gasoline you have, the farther you can go before you need to gas up again. The less gasoline you have, the less far you can go before you need to gas up again. And so that's also a positive correlation. Congratulations, you have finished this very long video.